This is the 7th video of Engineering Materials and Material Science Fundamental. In this lecture, we will see slip system and crystal structure of various materials. So here we have FCC, BCC and HCP crystal structure. So in this FCC there are 12 slip planes. In previous lectures we have seen what are planes and what are directions. So there are 12 different planes through which the atoms can slip. In BCC we have 24 to 48 such planes by which atoms can slip in different directions. In HCP we have 3 to 6 such planes through which atoms can move. Now, due to these 12 slip planes, FCC unit cell, the material are ductile because if we apply the load, the atoms can move in 12 different planes. That's why the material is ductile. Here in BCC, the material should be ductile because it has 24 to 88 slip planes, but we know that the atomic packing factor of BCC is 0.68, which is lesser than the atomic packing factor of FCC structure, which is 0.74. So what happens is there is a density difference. The FCC unit cell is more densely packed than BCC structure because it has more voids in a unit cell. 68% is occupied by the atoms and other rest space is empty. So the dislocation has to travel the dislocation travel has to gain more energy to change their atoms. We will look into dislocation motion later, but due to less density there is a distance between the atoms as compared to FCC. So what happens, we have to supply more energy to deform the material and to change the direction, change the location of the atoms in particular planes, and the motion of dislocation is requiring more energy as compared to FCC. So that is why it is strong and hard. It is not brittle because if we give more force it will deform. It will have characteristics because it has 24 slip planes. It will have a motion of the atoms, but it will not be like HCP where we have less number of slip planes. So the material has to be brittle, means material has to be broken to have motion of the atoms. So due to less number of slip planes it is brittle and hard. The atomic packing factor is same as FCC, but there is a significant decrease in slip planes. So the reason for BCC to be strong is its atomic packing factor, and the reason for HCP to be brittle, it is because the less number of slip planes. And we see the ductile behavior of FCC because it has 12 slip planes and it is more densely packed. Some of the examples of FCC are ductile materials like copper, nickel, silver, gold, aluminium, lead, and the gamma iron, which is austenite, which is in FCC phase for particular range of temperature. So when iron is at some particular range of temperature, it is in austenite phase, and which is FCC structure, so it is soft. These material are soft because of more number of slip planes. The BCC structure, which materials are strong and hard, are tungsten, vanadium, molybdenum, and alpha iron and delta iron, which we call as alpha ferrite or delta ferrite, which is the same variant of allotrope of gamma iron. So the iron has different microstructures. This property is called as allotrope or allotropy. So these three are the allotropes of iron carbon in fact. So this delta ferrite and alpha ferrite both are strong. So this particular question is very important, as why austenite is soft and why alpha and delta ferrita is strong and hard. In HCP we have magnesium, zinc and titanium. These all have hexagonal closed pack structure and they are somewhat brittle and hard structures. So now the real question, how the dislocation motion happens. So dislocation, we have edge dislocation and screw dislocation. So in this type we have here edge dislocation, and we know that Berger vector is perpendicular to this edge dislocation and the dislocation moves parallel to the Berger vector. So if we apply load in any direction, then this dislocation will, this same arrangement I have shown in grid method. So this dislocation is perpendicular to the Berger vector and this will move perpendicular to the Berger vector. So if we apply the force, this particular atom will pair with this and this will move further. So here there is a dislocation comes with these three atoms. Now again if you apply more load, this dislocation will pair with the neighboring atom and these three line will become dislocation like this. So this is how the edge dislocation glides through the crystal structure and it will accumulate at the grain boundary. So entire dislocation comes out from each and every crystal and each and every grain, and it will accumulate at grain boundaries, and after coming to grain boundaries it will stop moving and it will show some uh, strong and hard nature. So this is how the glide nature of edge dislocation comes into picture. In screw dislocation we have a spring like structure. So this particular edge, if we applied the load, this particular point will pair with this and climb motion will take place in edge and in screw dislocation, and this will form a perfect rectangular or square structure. Similarly this line will pair with the upper corner, and this is how all the planes of the atom will climb and forms a perfect rectangles. So the dislocation motion in screw dislocation is of climb nature and edge dislocation it is glide nature. Thank you for watching this video. If you like this video, then do share and subscribe the channel. See you in the next video with some more interesting topics in material science, and I'll cover some other subjects which are asked in such competitive exams, and I'll make the playlist. You can watch entire playlist or you can download the videos and use it for your reference. See you in the next video. Thank you guys.